What if we were asked to find the limit as x goes to 0 of natural log of 1 plus x squared minus x squared all over x to the fourth? This would actually be a pretty difficult problem if we didn't use Maclaurin series. So let us use Maclaurin series to be able to solve this. We need to find the Maclaurin series of natural log of 1 plus x squared. Now, if we remember, the derivative of natural log is going to be 2 to the x all over 1 plus x squared. And if we look at it from previous videos, this is the derivative, like that we could pull out the 2x and say this is 2x times 1 over 1 plus x squared. And then 1 plus x squared, like this, we do a u substitution with u equaling negative x squared. And we are going to get this is equal to 2x 1 over 1 minus u. And then when we know our power series, we're able to bring this down and say this is 2x sum of u to the n equaling 0 to infinity. Then we finally pull back our u substitution and say this is 2x sum of x equals 0 to infinity of negative 1 to the n, x to the 2n, which when we do our final substitution, we would get, or pulling the 2x into the series, we get the sum of n equals 0 to infinity of negative 1 to the n times 2 x to the 2n plus 1. Then when we take the antiderivative of this, we take the antiderivative because remember, this is equal to the derivative of that, then we are going to just get the sum from n equals 0 to infinity of negative 1 to the n, 2x to the 2n plus 2, all divided by 2n plus 2, which simplifies to the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 2, all over n plus 1. Now remember, because we did the antiderivative, we have this plus c out here, plus c, but at x equals 0, we get natural log of 1. So at x equals 0, we should have natural log of 1, which is 0. And we plug x equaling 0 here, we'll have a sum of zeros. So in order for this whole series to be 0, this c has to actually be 0. So we just get this series here. Now let's write out first couple of terms. At n equals 0, we get x squared over 1. Next term, at n equals 1, we get minus x to the fourth over 2. And then the next term would be plus x to the sixth over 3. Now, plus dot, 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 dot. If we plug this into the limit here, we'll see that we have an x squared, a minus x to the fourth over 2, a plus x to the sixth over 3, plus dot, 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 minus x squared. All over, of course, x to the fourth. Now, luckily, these x squareds cancel. And then we are left simply with x to the fourth over 2 plus x to the sixth over 3 plus dot, 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 dot. This is a minus here, sorry. And this is all over x to the fourth. And when we simplify, we take out x to the fourths, we're going to get a minus 1/2 plus x squared over 3 plus dot, 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 or higher order terms. Because all of these terms are going to be greater than x squared. And when we take the limit as x goes to 0, here is just a regular polynomial, so anything with an x in it will disappear. So this whole limit will just be equal to minus 1/2. So this limit, using Maclaurin series, can be easily shown to be negative 1/2. If you tried to do this without Maclaurin series, it would have not been pretty.